So now that I've explained what the timed memoizer's purpose is in the context of our scheduled executor service discussion, let's go ahead and do a deep dive into its implementation, and we'll really get to see how the scheduled executor service can be provided as a means to implement the timeout mechanism that we're going to use here. So we're going to show the implementation of the timed memoizer class. So as we'll see, timed memoizer is going to use the scheduled executor service to remove stale entries after the passage of a certain given designated time period. Timed memoizer implements function just like Memoizer did. That way we can use a timed memoizer transparently wherever we expect a function to be used. That's the beauty of Memoizers and the way we're doing it here with using Java 8 functional interfaces. Internally, we've got a concurrent map, which is implemented as a concurrent hash map, and that associates a key with a value that's produced by a function. And we put in another value parameter here, which is called ref counted value. And we'll see what ref counted value does as we go a little further along. What it's going to do is it's going to keep track of the number of times that a key value pair is referenced within the designated time period, which is M timeout in milliseconds. M timeout in milliseconds is the amount of time to retain a value in the cache. If a value is not accessed or if a key is not accessed within that time period, then it's going to be purged. We keep track of a field that stores the function that will produce the value based on the key. Then we also have an implementation of the scheduled executor service. This is going to use the scheduled thread pool executor, as we'll see in just a bit. And that, of course, is going to be used to execute runnables after the time period elapses. And it's also going to check for and remove expired keys based on the passage of time. And our final field here is kind of an interesting field. It's basically called M non-accessed value. And as you can see, it's a ref counted value that's going to have a ref count of 1. And we're going to use this in our implementation using one of the methods in concurrent hash map, the remove method, to very efficiently and in a thread safe way, check to see if a key has not been accessed within M timeout in milliseconds time. And if it has not been accessed, its ref count will still be 1. And that way we'll know it hasn't been accessed. Here's the ref counted value. As you can see, it's a nested class that records the number of times that a key is referenced within the M timeout in milliseconds period. And it's got some interesting features. It uses a field, which is an atomic long. We've looked at atomic long before. You did an implementation for a spin lock using a variant of this, using atomic Boolean or atomic reference, but basically the same idea. It allows us to atomically increment this count every time that a key is accessed. And we make this atomic because this could be called from multiple threads. And we want to make sure that the values are not corrupted. We have another field, which is called M value. That's the value that's being reference counted by the ref count we just looked at. And here's the constructor for ref counted value. As you can see, it takes the value and it takes the initial count and it sets the M value field to the value, and it sets the M ref count field to a new atomic long with the initial count. And then down here, we have a get method, and you can see what the get method does. Every time a get is called, it atomically increments the reference count, indicating that this value has been accessed within the time frame, and it returns the current value. And you'll see how this gets used when we look at the actual code in just a bit, which is really clean and really clever. Here's another very important method that ref counted value provides. This is called equals. And this is used by concurrent hash maps remove method to atomically determine if a key has been accessed within the M timeout in milliseconds time period. And as you can see, what it does is it goes ahead and checks to see if the ref counts are equal. So if the ref counts are equal, then this key value pair has not been accessed during the time period and therefore should be removed because it wasn't accessed. So it's perceived as being stale. If it was accessed, the ref count will be incremented by 1. And therefore, as we'll see, the equal check here will not work. It'll return false, and therefore we know that it's been accessed and therefore should not be removed. And you'll see how this gets used when we take a look at the remove method for concurrent hash map in just a moment. One final method on ref counted value. This is the schedule method. This is really kind of the secret sauce of the whole thing. And what it does is it schedules a runnable that will be used to remove the key from the cache if it's stale. And of course, it's going to be scheduled with the scheduled executor service, and therefore will remove it when the timeout goes off. So its schedule is given a key, and you can see it goes ahead and it makes a new runnable that has a run hook method, because that's what runnables do. And this is going to be used, this runnable will be used to check to see if the cached entry is stale, and will remove it if it has been become stale. So the run method will be called here by the scheduled executor service when the timeout elapses. So when M timeout in milliseconds elapses, then the scheduled executor service will automatically call the run hook method back, and then that's where all the fun happens. Now, one little trivia thing here, you'll notice that I use an anonymous inner class instead of a lambda expression. And the reason I do that is because I need to access the this reference within the context of the run hook method in this anonymous inner class. And for various reasons that are described in more detail in the link at the bottom of the slide, you can't access this from a lambda expression. And that's because lambda expressions really aren't objects. They're functions, sort of function-y like things, function-like substances, if you will. And therefore, since we have to access this, we need to make this an anonymous inner class object. So that's why it's new runnable. So here's how the run method works. And this is really subtle, super duper optimized, but somewhat tricky to understand. So the first thing we do is we come in here and we basically say, what's the current ref count for this ref counted object, for this value? What's its current ref count? And we're going to use this to do the staleness check. You'll see what the staleness check does in a second. So we get the old count. And then we go ahead and we try to remove the key from the concurrent hash map. Now, what's interesting about this, if you go back and you look at the equals method, which we defined back over here, equals only returns true if the ref counts are equal. So what that means in this context is if the key has a ref count that equals the M non-accessed value field, which always has a ref count of 1 because it never gets incremented, it's set in its constructor. That means that the key has not been accessed during this period of time, because otherwise its ref count would have been incremented, and therefore it's going to have a value of 1. In that case, we're going to remove it from the map because it was stale. Otherwise, it was updated. And so now what we're going to do is we're going to do a little bit of magic to try to atomically reset the reference count to 1, so it won't be considered accessed yet for the next time we register this remove if stale runnable. So what we're doing here is if it was accessed in the last time period, we're going to re-register it, and we're going to give it the appropriate ref count. And this is super, super cool as well. This is a very interesting method that's defined on atomic long called get and update. And what we're doing here is we're having to do all this little tricky code because of the inherent non-determinism of concurrency, and because of the fact that the concurrent hash map never locks all of its state. So there's no lock that locks the entire map. So what we're doing here is we're saying get and update. And what we're doing is we're taking the current count, which is whatever the ref count thinks is its current count, whatever its current count is. And we're checking to see if the current count is greater than old count. Remember, old count is what we set here when we first started this call. If it is greater than old count, in other words, if between the window of time where we got the old count, called remove, and now we're calling get and update, another thread came through and updated this particular ref count, we want to give it the current count because we want to take into account that somebody else has already incremented the value by 1. So it's been used in that time window. Otherwise, if it's not greater than old count, it's whatever it was before, and we just reset it to the value of 1. And basically the idea here is that ref count can increase concurrently by some other thread for the same key, since the concurrent hash map is never locked entirely. And that's both the beauty of the concurrent hash map as well as the complexity of the concurrent hash map. So we're just trying to make sure we give the right value for the ref count after these different stages. And then the last thing we do here in the run method is we go ahead and reschedule this runnable. In other words, we're using this again to run again in m timeout milliseconds. So it's saying schedule this runnable for this amount of time in the future and treat that as milliseconds. So that's how we reschedule ourselves. We use the remove if stale runnable to reschedule itself to run again in the future. And then the very last thing that happens in the schedule method is when the schedule method is called, after we set up that runnable anonymous inner class, we go ahead and schedule remove if stale to run at m timeout in milliseconds for the very first time. So that's the very first time it's going to run. And then once it runs the first time, then it's going to go ahead and call the run method on the new runnable that we made as the anonymous inner class. Very subtle, very tricky, but very cool. Let's wrap up the other key methods here. There's the constructor for TimedMemoizer, which is used to initialize all the fields. As you can see, we stash away the function, we stash away the timeout period. Then we create ourselves a new scheduled thread pool executor that has a single thread in it. And we go ahead and downcast the scheduled executor service to be the appropriate class, which in this case is scheduled thread pool executor. And then we set those shutdown policies that will remove the scheduled runnables and disable the tasks and get rid of stuff in the queue and so on. These are the sensible policies, not the default policies, which make no sense whatsoever. If you don't do this, then your program will crash in bizarre and mysterious ways. Here's the apply method. This, of course, is the key functional interface method that's going to be inherited from the functional interface, and it's going to return the value that's associated with the key in the cache. And what it does is it uses that super cool compute if absent method we talked about that's part of concurrent hash map. Remember, that's the atomic conditionally check then act method. And what it's going to do is it says, if there's already a value for this key, just return it. We're done. That call is thread safe. That's the happy path. That's the fast path. However, if there's not currently a value associated with the key, this is the code we're going to do. We're going to run this Lambda atomically to create, schedule, and return the appropriate new value. So let's kind of break down and see what happens in this case. So what happens inside of this Lambda expression is we make ourselves a new ref counted value object, which is going to apply the function to do the long running computation. And it's going to store the initial ref count, which will be 0 to start with, but we'll see in a second that it'll actually get incremented to 1 before we leave this particular Lambda expression. So this is a ref counted object, and this ref counted object actually runs the computation. And what we're going to do is we're going to go ahead and we're going to schedule this object that we just created, this ref counted value. We're going to schedule that to run in that many timeout in milliseconds time in the future. So what's happening here is a runnable is created for each key value pair that's passed the scheduled executor service, which could be excessive, and we'll talk shortly about how to fix that problem. The Lambda expression then returns the object that's associated with the key, and then what happens here is after this thing has been initialized, we then go ahead and call the get method on ref counted value. And if you go back and you look carefully at what the get method on ref counted value does, is it increments the count by 1 atomically, so it'll now have the value of 1, and it returns the current value. So that's how this whole thing gets initialized. So that's the end of the overview of how you would implement the runnable version of the TimedMemoizer, where there's a separate runnable for each key value pair. As we discussed, that's a bit excessive, so we'll look shortly at how to improve this so you don't have that particular space-wasting implementation characteristic.